This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good morning, everybody. I'm Joanna Albala. I'm the manager of the Science Education Program, and I'm happy to welcome you to Science on Saturday this morning, which is brought to you in collaboration with the Livermore Valley Joint Unified School District. So how many of you in the audience have come to Science on Saturday before this month? Oh, that is awesome. Well, welcome back. And before we get started, I'm going to go through my little introduction. Remember that if need be, if we have an emergency, please follow all the ushers' instructions. Let's take a moment to silence our cell phones so we can give the presentation our full attention. And please, when we're done with the presentation, would you please stay in your seats for the Q&A so that everybody can hear the questions and everybody can continue the learning process as our presenters answer the questions you may have after listening to them. So, this year's presentation, as you already know, Women in STEM, Science, Technology, Engineering, and Mathematics. And we've talked about science, and we've talked about technology, and we've talked about engineering, so we must be at math. And today we're going to talk about statistics in the world around us. And we're going to have a fabulous presentation. Our first presenter is Dr. Anna Kupresian, who is a statistician at the laboratory. She runs the group for applied statistics at the lab, and she's been at Livermore since 2009. She works on a variety of projects using her statistical skills, everything from stockpile stewardship to climate change, which you'll hear about today. And she received her PhD from the University of Arizona. Mr. Richard Newton is right from over the hill at Tracy High School. He teaches math and computer science. He got his degree in economics from UC Davis, and he is the chairperson of the math department currently. So without further ado, I'd like to introduce Dr. Kupresian and Mr. Newton. Thank you.
Morning, everyone.
Good morning, everybody. I'm here to help Anna talk about statistics in science. I hope that the talk is really engaging, and I'm really excited to have you guys learn about where math can be applied and in which ways to a variety of fields. And without any further ado, I'll turn it over to Anna. Thank you.
Thank you. I'm Anna Kupresian, and I'm an applied statistician at Lawrence Livermore National Lab. And if you don't know what that means, you will at the end of this talk. It's great to see you on Saturday morning showing up for Science on Saturday lecture. And we'll be talking about basketball, medicine, climate. And we'll see how statistics helps us understand everything around us. And Richard's going to join us. As Joanna said, this is the fourth lecture in the STEM series, where M stands for mathematics. And we'll be talking about mathematics of chance. In other words, probability and statistics. Through some episodes from History of Statistics, we'll see how statistics improves our understanding of the world and our lives. So how many of you have seen science, technology, and engineering lectures in the past 3 Saturdays? Quite a few. So what do you think Livermorium, iChip, and National Ignition Project have in common? Data. They collect data. They collect data and they have to do data analysis to show discovery of a short-lived element Livermorium. They have to do data analysis to study response of a human in a box to a particular drug treatment. Or they have to analyze data on already conducted NIF shots to inform what future shots they have to do in order to produce more energy and ultimately create a small star on Earth. You can ask, how do they do this? And the methods of data analysis have their roots in statistics, probability, and mathematics. Statistical methods help us analyze data, and to learn about the world around us. We humans, we've been curious about the world, including other human beings since day one. Collecting data and summarizing them with numbers has been our way of describing and explaining a world around us. The practice of conducting census began in Egypt in the 2nd millennium BC. They used census data for tax gathering and to determine fitness for military purposes. This collection of data for tax and military continued in many countries around the world to present times. Census in general means collecting data about every individual, person, or object. In contrast to census data are those data collected by measuring apparatus at selected locations and times. For example, imagine measuring temperature. We cannot measure everywhere all the time. This was especially not possible in the 17th century. When data are collected across large geographical regions and long time periods, it's important to keep procedures and records consistent. Otherwise, individual researchers might create records that are difficult to compare and reconcile. The first prescription on how to collect data and standardize weather measurements was given by Robert Hooke in 1663. This was one of early examples of statistics in public administration. It defines a standard for how data should be collected. While data analysis is the first thing we think of as a statistical goal, data collection is equally important. The earliest set of actual instrumental measurements of temperature date back to Medici network in 17th century. These data were recorded every few hours at 11 different locations in Europe, mostly through Italy, using identical thermometers. Even then, people recognized that weather can change within a day, and the measurements need to be taken several times a day. But in addition, they recognized that there might be something we call today measurement error. By the 18th century, the term statistics meant systematic collection of demographic and economic data. In the early 19th century, the collection of data intensified, and the meaning of statistics broadened to include all three disciplines: data collection, data summarization, and data analysis. Of course, in those days, there were no computers or calculators, so data summarization was done by paper and pencil. A pie chart, a form of graphical representation of data that we take for granted these days, was first developed in 1801. In 1834, the Royal Statistical Society was established in London. The members called themselves statists. It's a word we don't use often these days. And their original aim was procuring, arranging, and publishing facts to illustrate the conditions and prospects of society. The American Statistical Association, the main professional organization of statisticians in the United States, was established just 5 years later. And it's the second oldest continuously operating professional society in the United States. For 177 years, the association has been a close affiliate of the US government and the statistical work that is done in the government, in particular in Census Bureau, Department of Labor, and Food and Drug Administration. The first woman to be an elected fellow of the Royal Statistical Society was Florence Nightingale. Florence Nightingale was founder of modern nursing, statistician, and English social reformer. She was born in 1820 to wealthy English parents who discouraged her from pursuing the nursing profession. These periods are often known as dark ages of nursing, when nurses were unskilled and hospitals were merely places to die. So it's not difficult to see why her parents discouraged her from pursuing the profession. Florence loved mathematics from an early age and became a pioneer in visual presentation and information and statistical graphics. Florence became famous for her work during the Crimean War from 1854 to 1856. Responding to unpopular newspaper reports on horrendous situation in the English war camp hospitals, the Secretary of War agreed to let her organize a group of female nurses and to go to the war camp. In November of 1854, Nightingale and 38 nurses arrived to the British camp. The doctors originally did not welcome the female nurses, but as the number of patients escalated, their help was needed and they made a difference. Under Florence's leadership, the nurses brought hygiene, sanitation, nutrition, and comfort to patients. Her group of nurses transformed the hospital into a healthy environment within 6 months. And that resulted in the death rates of patients to drop from 40% to 2%. Nightingale is credited with a development of a form of a pie chart that we call these days Nightingale's rose diagram. This is a picture of a rose diagram from Florence Nightingale's report that she presented to the members of British Parliament on the nature and magnitude of the conditions of medical during the Crimean War. Now, if you look at the blue circles, the rose diagram on the left and the rose diagram on the right, they're on the same scale. And the area colored gray represents the deaths from preventable causes. The diagram on the right, starts with April of 1854 and goes clockwise. There are 12 slices on the diagram, and each slice stands for 1 month, and each slice shows number of deaths for that month. They're colored by causes of deaths, and you see that the gray area is the largest. So the majority of the deaths are preventable and due mostly to lack of hygiene, medications, and food. Florence and her nurses arrived to the camp in November of 1854 and start implementing changes to the nursing practice. 6 months later, the mortality rate drops to 2%. We see this on the diagram on the left. So Nightingale's statistical data analysis strongly influenced the findings of the commission investigating the health in the British Army and resulted in greater public health advances. Nightingale was described as a true pioneer in the graphical representation of statistics. The kind of data that Florence collected in military hospitals we refer to as observational data. In contrast to observational data are the data collected from experimental studies. In the 20th century, statistics began to be used in pharmaceutical testing. When a new drug is introduced, the question that needs to be addressed is, does it work? More precisely, how effective is the new drug in treating certain medical condition? We want the drugs to be effective for a large population, but it's not possible to test them on the entire population. So the question becomes, how should an experiment be designed to test the effectiveness of a drug? Statisticians established a procedure called randomized controlled experiments. First, the subjects are selected to represent the population of interest. Then the subjects are randomly assigned to 2 groups, the treatment group and the control group. The treatment group is then given a new medication or treatment, while the control group doesn't receive the actual medicine, but a placebo. Statisticians then use a method of comparison to compare the effect of the drug. The reasoning is, if the control is comparable to the treatment group, apart from the treatment, then the difference in the response of the two groups is likely to be to the effect of the treatment. The random assignment of subjects is used to make sure that the treatment group is like the control group. In a double-blind experiment, subjects do not know whether they are in the treatment or in the control group. Neither do those who evaluate those responses. This guards against bias both in the response in the evaluation. When the response of the two groups are compared, the question becomes, is the difference between the two groups due to chance or something else? Just as important is the question, if there is a difference between these two groups, what is the chance that we see it? Statisticians have invented tests of significance to deal with these sorts of questions. The reasoning behind tests of significance relies on understanding of probability. Probability is part of mathematics that studies questions about chance and events happening. People talk loosely about chance all the time. What is a chance of getting a job? What is a chance I meet Steve Curry on a street today? Or what is the chance of rain tomorrow? But for scientific purpose, it is necessary to give the word chance a definite and clear definition. This turns out to be hard, and mathematicians have struggled with this for centuries. The doctrine of chance was the first textbook in probability, and it was written by 18th century French mathematician de Moivre. Moivre wrote of the chance of something as a percentage of time it is expected to happen when the basic process is done over and over again, independently and under the same assumptions. So if we flip a coin many times, half of the tosses will result in heads, half of the tosses will result in tails. If something is impossible, it happens 0% of the time. So if we were to roll 2 dice and add the numbers, could we get 14? No, because on each of them the largest number is 6, so the largest number we can come up with on 2 is 12. So that's an example of impossible event, getting 14. On the other hand, if something is sure to happen, like the sun rises tomorrow, then it happens 100% of the time. Testing the effectiveness of a new drug was just one of the examples of statistical reasoning being used in public administration. There are many more. And with the emphasis on learning from data and making better predictions, statisticians have been working in government, business, science, and even sports. And I'll turn to Richard now to tell you how statistics is used in basketball.
Thank you. Thank you, Anna. So it's a really exciting time in basketball right now because data analytics and statistics are transforming the way the game is looked at and how it's being played. And the reason for that is because up above each basketball court are now 6 cameras, which are recording the movement of all players in 3-dimensional space. And from that data, you can generate hundreds of thousands of data points because you have 5 players per team, as well as the basketball that represents 11 actors across about 5,000 square feet of floor space for 48 minutes. So with that data, we can now start asking more advanced questions than we could previously. Previously, we only had a box score, which represented about 5 statistics: rebounds, assists, points, steals, and blocks. So what I like to call this is high-resolution data. The problem then becomes, how do you take that high-resolution data and then take it and answer questions with it? So we're going to go to YouTube, And we've got a video clip that explains how the Golden State Warriors are using data to transform the way they look at the game of basketball.
The Warriors are the top seed in the NBA playoffs, but their success is predicated on much more than jukes and jumpers. They rely just as heavily on tracking and technology.
We have the SportView cameras by StatSync here.
6 of them strategically mounted high above the Oracle court.
Basically allows us to map out the game in a three-dimensional everything.
Everything from player positioning and ball movement to shot charts and tendencies. The data and its applications seemingly limitless.
We've got data from every single game during an NBA season. We kind of do whatever we want with that data and manipulate it in a way that makes sense, and we can ask the questions and get answers.
Stop. That's the shot we want.
Enter Sammy Gelfand, affectionately known as
Cruncher the Wizard. A lot of different nicknames depending on the day.
His official title is Coordinator of Basketball Analytics. His job, to take the mounds of SportsView data, use it to formulate the right questions, help answer those questions, and disseminate the information to coaches and players.
I'll go to him and ask him for maybe a certain stat that I'm looking for, or maybe something I'm seeing on the floor, and I'll ask him if there's a stat that he has that can either support or deny the argument.
You have to narrow the field down. You don't just take a bunch of data and like picking a needle out of a haystack. When you watch the games, things will pop out. Sometimes we'll get answers that we can make decisions from. Sometimes we won't.
Those decisions might be as minor as which direction to force an opposing ball handler, or as major as which player might add the most value to the organization, especially when it comes to defensive metrics that are harder to quantify through traditional statistics.
I've been told a couple of times that was the main reason why they traded for me, was to shore up our defense. They invested a lot of time and resources in researching that. I knew they were researching me a month before the trade deadline.
So what I really like about that video is it highlights how they're taking the data, but it takes a statistician to analyze that data to inform decision making. And they use those decisions to guide what's happening on the floor during a game, to plan for a game, or even in the middle of a game to maybe change at halftime the approach that they're using on the fly. Additionally, they use that information to guide the decision-making process of the organization in terms of which players they want to acquire, maybe which players they need to get rid of. And so we have another video which I think is really interesting because it demonstrates that if you consider the Golden State Warriors organization, it's probably worth about $2 billion or more today. And so these decisions are incredibly important from an economic standpoint. So this next clip is actually the Golden State Warriors COO, or General Manager of Basketball Operations, explaining how they're using analytics and statistics to guide their decision-making process at the highest levels.
Basketball, it's not just about our customers, okay? Big data is affecting the game on the court and how we gain a competitive edge. Technology is increasingly making an impact on the basketball court. Gone are the days of assistant coaches just counting points and rebounds and assists. Today it's about efficiency. In the amount of time I'm given on the court, how efficient am I in scoring points? What combinations of players playing together perform best in each game situation? Is the play more effective when a star player catches the ball and shoots immediately, or dribbles twice and then shoots, or drives to the basket? The Warriors were really one of the first teams to deploy the most advanced product available to get objective answers to these questions through analytics. Up in the rafters of Oracle Arena, 6 cameras are deployed to capture every movement of every player on the court. We're going to show you a video that we've slowed down a little bit to make it easier for you to watch. As you can see, each of these players is identified with his jersey number. One team's in yellow, the other in red. The red circle follows the ball. Each player's position is tracked, his activity recorded, each dribble, each pass, each shot. Then we have a 3D map of every player and every combination of players sharing the court at the same time. We can actually, at this point, analyze how the offense develops each play and how the defense defends the basket, represented here by the blue and yellow. Now, hundreds of thousands of data points are represented, and then they're organized into reports that our coaching staff can use to improve team performance. And we're really just scratching the surface at this intersection of technology and the game itself.
I really like how he concludes there. I also like how he's taking the data and they show the mathematical or physical model that they're generating. But what he says at the end is really powerful, that we're really just scratching the surface of the intersection of the technology and the game of basketball, because we're able to now gather all this data, but what do we do with it and what decisions can we generate? And I want to show you how it's changing the nature of the game in a couple quick steps. So if we look at this first slide here, what you can see is when the three-point line was entered into the NBA in 1979, very few teams took three-point shots. You can see the graph represents the number of times a team attempted a three-point shot per game on average. So in a particular season in 1979, teams only tried three-point shots per game, which is extremely low. Today, they're taking 22 shots per team per game. So there's been an increase by a factor of about 7. We can actually see right here, they shortened the three-point line during a couple of seasons and teams took more shots. But if we were to account for that aberration in the data, we would see a strong linear trend. So the decision is being made to take more three-point shots. And the question would be, why are they making that decision? And then it's also influencing the behavior, not just of the teams as entities, but as the individual players. So on this next slide, what we're going to see is anyone that's been listening to the news these days is probably hearing that Stephen Curry is extremely close to breaking the record in number of threes made per season. We can see that record being beaten here in 2 consecutive seasons. So let me explain what the graph is demonstrating. In the blue, you can see Jones in 2005 set the record for most threes in a season with 225. And the graph is showing from the first game of the season to the final game of the season. So we're going across the games, across the x-axis. And we can see sometimes he was making more, and then sometimes his rate slowed down, but he ended up at 225. Last season, Steph Curry broke the record with 286. So we can see the growth over the course of the season in his number of shots made. The yellow represents his pace as of this season, as of a few weeks ago. He's actually about to break the record in a couple of games. He's just short of 286. So the question can become, then where is he going to go moving forward? We've taken the data, we've collected it, we've analyzed it, we've summarized it graphically, but now we can use it to make a prediction. How many three-point shots is Stephen Curry actually going to make this season? And so various people are trying to guess how many he's going to make. And so if you make an approximation or a prediction of, let's say, 403 3-points made at the end of the season, that wouldn't be a very good prediction because it's so specific. All right, so instead of making an extremely specific prediction, I could do something like this, and I could have a cone of variability in my prediction, stating that at the end of the season, I think that he's going to have somewhere between, say, 380 shots made and 430 shots made. All right, this is powerful because this is not a form of weakness in my argument, and a lot of people see mathematical uncertainty in that way. Instead of being a weak argument, it's actually now a strong argument, because if I said he's going to make 403 shots, my likelihood of being inaccurate is extremely high. If I give a cone of variability in my prediction, I have a very strong prediction that's going to be more accurate a higher percent of the time, so I can be more confident in that prediction. So the decision-making process is changing over the course of a season, but how does that affect an individual shot being made? And that's another question that we could look at. This next slide is purposefully overwhelming. All right, so this represents all of his shots from every region of the floor up until now in the season. So there's various regions represented, and I'm going to highlight one. So we can see up until now in the season, he's taken 270 shots from this particular region of the floor and made 163 of them, giving him an accuracy rate of 60% from that space. Whereas this is his worst spot on the floor. He's taken 16 shots and only made 6 of them. So he's 38% from that region there. So I can take this information, which is maybe too much to look at broadly, and narrow down the scope of my question by doing something like this. If I look only at the difference between making an easy shot close to the basket, where he's 60% accurate, and I summed up all the shots from beyond the three-point arc, and he's made 222 out of 488 shots, we can see that he's 45% accurate from far away, and 60% accurate from close to the basket. But it's still not answering questions on his decision making. I know now that he's less accurate from far away, but that seems like an obvious answer. So we could break down the question a little bit further. And what I'm going to do is I'm going to change it to have a like denominator, because right now it's confusing. He's taken more shots from far away than close up. So if I change it to having a denominator of 100, now I can see, were he to take 100 shots from close to the basket, I would expect him to make 60 of those shots. So that represents my ratio of 60%. Whereas if he took 100 shots from far away, I would expect him to make 45. All right, but at the title of the slide, it says that we are generating expected points, not expected ratio of makes to misses. So we know that he makes more points if he's further away. So the analysis I'm doing leads to this conclusion. In terms of points, were he to take 100 shots from far away, he would make expectedly 45 of them, according to my ratio, and he would get 3 points per shot, giving me 135 overall points. Whereas if I gave him the ball and he shot it from close up 100 times, I would expect him to earn 120 points. Well, now it looks much more clear in guiding my decision. Should I take a 2-point shot or a 3-point shot? And it seems from this graphic that I should be going for the 3-point shot. So this guides my decision-making process in giving me expected points per possession when Stephen Curry is holding the ball, given he has the choice. But that's not the whole story. All right, this is an expected points value breakdown. And really, there's a nature of probability that's going to go into whether he makes or misses those shots. So what we've done now is we've taken that information and we've put it into a simulation. And I've broken the simulation down into two worlds. On the left side of the world, you can see the pink Stephen Curry. He's behind the three-point line, and he's going to attempt a three-point shot. So he's got a 45% chance to make the shot, and if he makes it, he gets 3 points. The Stephen Curry on the right in purple is going to attempt a 2-point shot, which we know he has a 60% chance to make, and he'll earn 2 points. We're going to give each Stephen Curry 10 shots, and he'll either make them or miss them. So on the left, if he takes 10 3-point shots, he could earn anywhere between 0 and 30 points. And on the right, he could earn anywhere from 0 to 20 points. So I'm going to have a student volunteer of mine come out and help me. This is Bella. All right, and I'm going to let Bella actually pick if she wants. So Bella, you can come on over here. So do you want to attempt the 3-point side or the 2-point side?
I'll do the 3-point side.
You're going to go for the 3-point side? All right, so you can take the chair on the left. So before we engage in the simulation, I want everyone to make a prediction. All right, given 10 shots for each Stephen Curry, which one do you think is going to earn more points? So if you think the Stephen Curry on the left, the 3-point shooting Stephen Curry is going to earn more points, raise your left hand. And if you think it's the one that's taking the 2-point shots, raise your right hand. Okay. All right, so I'll let Bella shoot first, so we'll wait, Bella, just 1 sec while they get it going on the big screen. All right, cool. So she took her first shot, and you can see didn't make it.
Oh.
All right, I took mine, didn't make a shot. Oh. Uh-oh, I'm in big trouble. Oh, tied it up. All right, looks like I'm in the lead. Oh, there we go. Oh, yep, that's it. So 10 shots. So it looks like the 2-point side won. So just raise your hand really quick if you got the right prediction. All right, so that kind of contradicts what we had previously learned, which is really interesting. And what's really nice about computing is I can now do something like this. That was rather slow. So what I've done is I set up the computer to run 1,000 trials of this experiment. So there's going to be 20 shots, because 10 shots per player, times 1,000 is 20,000 shots, which is about as many 3-point shots that have been taken this last month in the NBA, to think about a scale there. And I'll just run the simulation. And there we go. So that was 20,000 shots, and we can see while in our single trial, the 2-point shooter won, In the long term, in the very long term, like Anna's been talking about, we would actually expect the three-point shooter to win more frequently, and there are some ties. So hopefully that clarifies the idea of expected value and the nature of probability, and how additionally simulation can be extremely powerful in guiding the decision-making process. So if everyone could give Bella a nice big round of applause, that'd be great. Thank you, Bella. All right, and with that, I'm going to turn it back over to Anna so she can show you how big data decides her decision-making process in the field that she works in. Thank you.
Thanks, Richard. So it looks like there is a lot of data generated in basketball when the spatial position of each player and the ball are tracked over time. However, there are natural phenomena that generate much larger data sets. Can you think of one? For example, the Earth. Climate scientists study our enormously complex planet, and they employ statistical reasoning to make sense of the data. If you want to learn more about climate science research, you can find several lectures given in the Science on Saturday series by climate scientists. I'm a statistician, so today we'll talk about climate from data perspective. We'll talk about uncertainties. And uncertainty doesn't mean we don't know anything. It doesn't mean that science is not reliable. On the contrary, to a scientist, statistically calculated uncertainty is a form of knowledge and explains how well something is known. People often think that weather and climate are the same, but they are not, right? The weather is the state of the atmosphere around us, and we can measure it with instruments. We can measure temperature, pressure, humidity, precipitation. The picture on the left shows weather conditions in Livermore yesterday. The picture on the right could represent climate in Livermore in February. Sometimes it's cold, sometimes it's hot, but more often it's between. Weather happens day to day and in short term. Climate is weather over a long period of time. There is an old saying, climate is what you expect and weather is what you get. We can think of climate as the probability or chance of different types of weather occurring. Climate change is change in the typical or average weather. For example, increased average temperature may mean many more hot days and slightly fewer cold days. Now, if you are flipping a coin to see if it's fair, you need to flip it for a long time before you can be sure. In the same way, we need decades of weather records to make statement about climate. To study climate and detect change, we need observational data. With advances in technology, we can collect data from deep oceans to atmosphere. For example, some NASA satellites and instruments observe Earth's land, air, ice, water. Others monitor the sun and the amount of energy coming from the sun. They're all important for understanding how climate works. From scientific view, we need to survey all the data, not just temperature records from the surface or from space, but also data from deep oceans, Arctic sea ice, land-based glaciers, Greenland, and so on. There are many very difficult problems that statisticians work together with climate scientists. One of them is that observational data from different measurement platforms often represent climate processes at very different spatial and temporal scales. Lab scientists and statisticians are involved in research that studies how what is the best way to combine the data that come from different sources? How to identify and adjust for differences in measurement systems, and how to deal with change in spatial and temporal coverage of measurements. This is the map of observed surface temperature change from 1901 to 2012. This map was derived from temperature trends determined by a statistical method called linear regression. One of the challenges we face is that in early 20th century, we don't have observations from many parts of the world. Those areas are white on the map. You see on the map that the air temperature over land changes more because the change in temperature over land happens much more rapidly than the change over ocean. Over parts of the ocean, you see that the change is around 0.5 degrees Celsius, while over land, you see regions colored in purple with the change of 2 degrees Celsius. Many aspects of climate are showing evidence of change. Here is a graph that shows increase in global land surface temperature from 1850 to present time. Each curve represents independently estimated change. And while all these curves are not the same, they don't completely agree. We see that there is upward trend in all of them. We see similar upward trends in the global sea surface temperature. On this graph, there are 5 independently derived estimates of sea surface temperature. We like to have many little Earths to play with and collect data. We don't have them. So we need computer models to simulate the Earth. Climate models are computer programs with mathematical equations. The heart of a climate models are the basic laws of physics, like Newton's law of motion. Climate models use mathematical equations to describe behavior of various factors of the Earth system that impact climate. These equations describe sun's energy, dynamics of the atmosphere, ocean, land surface, living things, and ice. The models are programmed to simulate conditions over hundreds of years as accurately as possible. To solve all these mathematical equations, we need supercomputers. And here at Lawrence Livermore National Lab, we are fortunate that at any given time, we have the fastest and the biggest supercomputer in the world. Now remember, we said that when we talked about sampling from the population, we said that we cannot test every possible subject. Similarly, when running simulation experiments on Earth, there are too many different experiments we can try even for a supercomputer. So the question is, how do we choose ones to run? This is where statisticians come in to help select the most useful simulations to run, those that will give us the most information about the questions we are interested in. Climate change is caused by change in energy balance. There is more energy coming into the system than coming out, and the planet is storing it up. The extra energy means that the temperature is increasing. On this graph, we see increase in the observed temperature shown in the black curve. The question that we can ask ourselves now is this increase due to nature alone? Well, we have climate models and we can run computer experiments. So the red curve shows what our computer model tells us if we assume that there is no human factor influencing the climate. Actually, this graph shows temperatures from many such simulations in gray and yellow. And you see that none of these simulations agree with the observational data. And remember, we run all these simulations under assumptions no human factor influences the climate. Therefore, warming cannot be explained by nature alone. What if we change the simulation to include human behavior? If we look at simulations that take carbon dioxide and other human factors, now we see that the simulations are pretty close to the observed temperatures. So the fingerprint of human activity is relevant to the magnitude and patterns of the observed climate change. The question is, how fast will the warming be? And what happens to the right of this graph? What happens past 2010? Here we see possible future trends of temperature. In red, we see what simulations predict if we continue greenhouse emissions at the current rate. In blue, the simulation assumes that we'll go green. Each of these predictions has its own cone of variability. In fact, we don't know with certainty how humans are going to behave in the future. So we have to consider many scenarios. What if we continue to produce emissions as we are now? What if we manage to reduce them in the developing nations? We are not certain at what rate the world's population will grow. What mix of renewable and fossil fuel will people use in the next 50 years? So assumptions about all these questions influence the prediction of future climate change. I hope that we convinced you that you can apply statistics to many different areas and that through statistical analysis, data have been telling us fascinating stories through history. I'll quote one of my favorite statisticians, the great John Tukey, who said once, "The best thing about being a statistician is that you get to play in everyone's backyard." That pretty much sums up why I ended up a statistician. I like working with other scientists, learning other science, what they do, and looking at the data. Even better, it's a great time to be a statistician. Computers make it possible to do things with the data that were unimaginable before. But they also create so much data that we need all the statisticians we can get. Statistics is the 9th fastest growing occupation, and it's likely to be ranked even higher. So my plea to you, the next generation, is take statistics classes and learn kind of skills needed to succeed in data-centric world. This is the end of my talk. Thank you all very much for coming today. Please stay in your seats and we'll take questions.